Okay, let's talk about rational functions. So here's an example of when a rational function might come into play. James, an artist, he wants to start a card making company. The startup cost would be 5,000. He's got some good cards and he's going all the way. And the cost of producing a box of cards is 650. So we'll write the total cost C as a function of X, where X is the number of boxes of cards made. Okay, so let's see. We're going to write the total cost C as a function of X. Okay, and X is the number of boxes of cards made. So here's my $5,000 startup fee. And then it costs 6.5 for every box that I make. I'm sorry, 650, but I'm going to write 6.5. Okay. Okay, now you say, but Marge, that's linear. Yes, that's a linear function. So here's how we get the rational. Average cost per box. Now C with a bar on top is actually the symbol for average as a function of X. So when we find the average cost per box, then we'll find the domain of the function. So the average cost would mean if I take all of these, so here's my average cost. If I take a whole cost, 5,000 plus $6.50 for each X, and divide it by how many boxes I actually make, then it's only costing me so much per box. Okay, so that's the average cost function. Now the domain of that, let's see, X is number of boxes. So we really can't have, well, we could make none, and that would be ridiculous. We could make one, we could make two. We can't make fractions. We can't make 1.5 boxes. We can't do that. So let's just basically say we want positive and we want integers. And so we could just say the domain is the positive integers. Okay. And then it says, okay, use your function to find the average cost per, whoops, let's go back, to find the average cost per box when there are 10 boxes made and 100 boxes made. Okay, so suppose I only make 10 boxes. That would be C of 10. All right, so I'll have 5,000 plus 6.5 for 10. And then I'm going to divide it by the 10. Okay, if you do this on your calculator, you'll see the 5,000 plus 65 divided by 10. Wow, that's 506.5, which is 50 cents per box. That's costing me a lot. Let's see if I make 100. So that would be 5,000 startup plus 650 for 100 boxes, and then divide it all. Let's see if I can get that cost down a little bit. So that becomes $56.50 divided by 100, which is, oh yeah, $56. It's still not great, but it sure is. The more I make, of course, the more I sell, the less I'm going to have to, it's going to cost me. Okay, so let's look at the graph. A table of values for this function and to verify. So I do have Desmos already here. So we'll go to our Desmos graph. And you can see in I put the function in and then I hit table. And we've got the table of values there. And sure enough, here's my 10 for $506.50. And there's 100 boxes for $56.50. So I verified my answers here. Okay, let's go back to the lecture. All right. Now, rational expressions and functions result when a polynomial is divided by a non-zero polynomial. Okay, so expressions and functions. A rational expression and function result when a polynomial is divided by a non-zero polynomial, because we can't divide by zero. Okay, so we can't have that. So example would be right here, you have 5 over x. That's technically a rational expression because we have a polynomial over a polynomial. Okay, those are little polynomials, but they're true. Okay, so basically it's a fraction with expressions in both the numerator and the denominator. Okay, so we're going to be working with these. Let's talk about different ways we can see rational functions. You can have a table of values, and here's our equation. So let's go ahead and look at the function 1 over x minus 2, and we'll complete this table of values. If x is -1, that would be 1 over -1 minus 2, or 1 over -3. Okay, if x is 0, that would be 1 over 0 minus 2, or -1/2. If x was 1, I'd have 1 over 1 minus 2, or 1 over -1 is -1. 1 over 2 minus 2 is 1 divided by 0. No solution. That's a sad face. I should do it mathematically. Okay, there is no solution. 3 would be 1 over 3 minus 2, which is 1 whole. And 1 over 4 minus 2 gives me 1/2. Okay, so let's plot a few of these points. -1, -1/3, 0 is -1/2. 1 is -1. 2 is no solution, so actually that's where we're going to have an asymptote. I can't say all, but almost all rational functions will have a vertical asymptote, which is a domain restriction. And then a vertical asymptote just it guides the function, hey, come this way. And so this vertical asymptote is actually going to guide this function to go that way. And this will go here. Okay, let's get the rest of our points. 3, 1, 2, 3, 1, and 4, 1/2. And if you could plot more points, but I can see that this asymptote is guiding it to go up this way. Okay. So that's what our graph looks like. For which value of x is the output undefined? As we found out, x cannot equal 2. And so the domain of this function would be from, if you remember the domains, we're going to talk about the x-axis and which values on the x-axis. So we're going to go from -infinity all the way to 2, and then we can't have 2, so it's going to be -infinity to 2, open because I don't want to, and open again on 2 to +infinity. Okay, I could also say the domain is all x such that x is a real number, but x cannot equal 2. Okay, all right. Now, let's evaluate some rational functions. So we can use either the formula, this graph here, or this table to evaluate the following function. So if we want to find f of -2, I'll use the formula. So that would be 3 times -2 over -2 minus 1. -6 over -3 reduces to a 2. So let's, f of -2 equals 2. Let's use the graph. F of -2 equals 2, yes. And let's use the table. F of -2 equals 2. Okay, let's do f of 1. 3 times 1 over 1 minus 1 is 3 over, that would be no solution. And let's look at the graph. Sure enough, there's our asymptote right here, okay? And if we put in 1, there's our no solution. And let's do one more. 3 times 2 over 2 minus 1 is 6 over 1. So f of 2 should be clear up at 6, yes. And f of 2 is 6. There we go. So the domain of this function is everything except 1. So we'll go from -infinity to 1, omitting 1 to +infinity. And the range, wow, that's the y values. So the range is, if you're going to see this right here is a horizontal asymptote, and I can see that because it's getting really close to this, but it's not touching it from both directions. So I'm going to say that y cannot be 3. That's my domain, okay? All other values except 3. All right, so now how can we find, whoops, don't need that. How can we find the domain of a rational function without a graph first, and then we'll check by graphing, okay? So identify the domain, and then we'll check with the graph. So first of all, the only thing you need to look for in these are if we can't divide by 0. If you recall domains, restrictions, you can't divide by 0. So just look at the denominator. 8 will never be 0. And so there is no domain restrictions. We're going to say the domain are all real numbers, or negative infinity to infinity. Now this domain, on the other hand, x minus 2, not okay. X minus 2 cannot equal 0. So let's find that asymptote in this case by solving for x. So when x equals 2, we're going to have an asymptote. And so the domain is going to be from negative infinity to 2, and then 2 to infinity. We are not having the value of 2. And here's another one. Uh-oh, we got a quadratic. Now what we need to do is find out when this denominator is equal to 0, because those are our most likely asymptotes. There are also holes. We'll come up to that soon. So let's factor this, because we need to solve this equation equal to 0. So x times x, 3 times 1, and we have a negative 3 plus 1 gives me the negative 2 right here. All right, so to solve this, I would say x is 3 or x is negative 1. So it looks like there might be 2 asymptotes. So this is going to be tricky. Ready? We're going to go from negative infinity to negative 1, from negative 1 to 3, and then from 3 to positive infinity. And that gives me all of my domain. In other words, watch out for those 2. It's everything but. Okay, so now let's check these 3 solutions on Desmos. So the first one was everything. The second one was 1 asymptote at 2, and the third one should be 2 asymptotes. So let's go back to my Desmos, and we'll get rid of this guy. Okay, so here's the first guy. And we want to change that. Let's change our grid, because we don't need to go up to 4,000 on this. Let's just go 10 by 10s. Let's go 10. Let's see, I've got to do this. And so what we're going to do is, here's a little lesson on getting a good viewing window. All right, so let's put okay. Sometimes the whole thing lights up if you just type in 10. And let's go right here. Let's on this, and we'll go negative. There, see the whole thing lit up there. And then same thing with the y-axis. Let's just positive on the high, negative 10 on the low, and I think we'll be okay on this. Okay, so if you see this is a linear graph, so there is no problem, no domain restriction. On the second one, let's close that and open this. We said there was probably going to be an asymptote at 2. And there we have, I'll go ahead and scrunch this up so we can see that this is 2 right here. Okay. Matter of fact, I can graph that asymptote. It would be x equals 2. And there you go. There's the proof. Okay, and then the last one we said might have 2 asymptotes. Let's look at that. Oh, check that out. And those asymptotes were, what were those asymptotes? I think they were negative 1. Let's see if that's right. Yep. And the other one was 3, I believe. X equals 3. Oh, can't do both of them, I guess. We'll go to the next one. X equals 3. There we go. There's the proof. Okay. All right. So back to this lecture. We have one more, and then we'll be done with this. So hang in there. This is just using technology to solve the problem instead of algebra, and that's always fun. So the concentration of a drug in a patient's bloodstream in milligrams per liter can be modeled by this function. T is the number of hours since the drug is injected. answer the following questions with technology. Okay, so C is the concentration, and T is the number of hours since the person had the drug. So what is the concentration after 10 hours? And we need to know how many hours. Well, let's just do 10 hours. So first of all, let's look at the graph. I've got this for us here so I can write on it. Okay, so I typed the function in here. And instead of T, I'm using X because it's Desmos. So this is T. This is the number of hours since they were injected. Okay, and then this is the concentration of drug in, I think it was milligrams per liter. Okay, so concentration on the y-axis. Okay, so you can see if we start at 0 right here, okay, we don't give the drug, then the concentration is nothing. But after this long right here, and that is at 2, that's this right here. So after 2 hours, there's 1.8 milligrams per liter. And after 10 hours, there is, here it is, 0.849 milligrams per liter concentration in the bloodstream. Okay, so by graphing this, and by the way, to make this graph happen, I had to use this table to look at the values and how little they are, and then I changed the x-axis, the y-axis. The x-axis was fine. The y-axis, I just had to make it smaller so I could see that. So when they ask us, what is the concentration after 10 hours, I'm going to put about 0.85 milligrams per liter. And then so many hours after injection, the drug's concentration is at the maximum value. And that's going to be this, because that's the highest. So we're going to say 2 hours since injection, the drug's concentration is at 1.8 milligrams per liter. Okay, and that's the end of this video. So you can practice these skills in your homework set.